So now we need to connect the features of a graph and its derivative. So far we've looked at graphs alone and critical points, which come from a derivative, but now we need to tie those together. So down below, this function g of x, we're asked to describe it at the point x equals -2. So when we look at -2, we look up towards our graph and we can see that we have a relative max when the function is at -2. So now, if we look to the left of that -2, we can see our graph is headed upward, which means the function itself is increasing. And the derivative, which is the slope of tangent lines in this region, are positive because all of these slopes are headed upward. Now, when we look to the right of -2, we can see that the function itself is headed downward, so the function is decreasing, and the slope of all points in that region are negative because they're headed down when viewed from left to right. And now we're asked to do the same thing at +2, so we find +2 on the graph. We can see that this region has a relative minimum. And again, we look to the left of x equals +2 and see that the graph is declining as it gets to +2. So the graph is decreasing and the slope, which is the derivative of all points where I've written the purple line, are negative. Additionally, when we look to the right of +2, then we can see that our graph is headed uphill, which means the function itself is increasing, but the slopes of all derivatives, the slopes of all tangent lines, which are the derivative, are positive. They're headed uphill. So the whole focus of this section is actually on what's called the first derivative test, but we need to lead into how we look at it. So suppose we have some point C that we've determined is a critical point. Doesn't matter whether it was singular or stationary, it's a critical point. And so long as there is some x value that's close to the point C that's our critical value, and we can have a derivative exists, then what we have found is if the derivative is positive, that meant the graph is increasing to the left of our critical value. And if the derivative is negative to the right of our value, our graph is headed back downhill. So this means our function f has a relative max. If we go from uphill to downhill, we can see that we've climbed over a mountain, so we have a maximum at the critical point C. Mine looks like -C, but it's an equal sign. So next, that derivative instead, if when we were looking to the left of the critical point, it was negative, we had been walking downhill. And now when we look to the right, if we have a positive derivative, this means we're walking uphill, then our function has a relative min. If we go from downhill to uphill, you can see that we pass a valley, which would be a low point or a relative min. Now, super important that we went from up to down or down to up. What if that doesn't happen? What if the derivative has the same sign on both sides of that critical value? That means that critical value where the function is has neither a relative max nor a relative min. So two important points to tie this together. The key is that we need to look at both sides of C, our critical value, and if the derivative changes signs, then that critical value is extrema, maybe a relative max, maybe a relative min, depends on what sign changes our derivative has. But the last important piece is that not all critical points are extrema, right? That's what we just said. If we have the same sign, it's neither a max or a min.